Imagine turning on an old television late at night when no stations are broadcasting. You see that familiar static snow dancing across the screen, right? Well, here's something that will absolutely blow your mind. A tiny fraction of that static, about 1% of it, isn't coming from electrical interference or random noise. It's actually ancient light from the very birth of our universe, traveling through space for nearly 14 billion years just to reach your living room. This is cosmic background radiation, and today we're going to uncover one of the most incredible discoveries in human history that completely changed how we understand everything around us. You know, when I first learned about this, I couldn't sleep for days. The idea that we can literally see the afterglow of the Big Bang just by looking at television static seemed too incredible to be true. But it is true, and the story of how we discovered this cosmic fingerprint is filled with accidental discoveries, Nobel Prizes, and revelations that shook the scientific world to its core. So what exactly is cosmic background radiation? Let's start with the basics and build our understanding step by step. Picture the universe when it was incredibly young, just about 380,000 years after the Big Bang. Now, 380,000 years might sound like a long time, but in cosmic terms, this is practically the moment of birth. At this point, the universe was unimaginably hot and dense, filled with a soup of protons, electrons, all bouncing around in what scientists call a plasma state. Think of it like being inside a thick fog where light can barely travel anywhere because it keeps hitting particles and getting scattered. The universe was essentially opaque, meaning light couldn't travel freely through space. But then something remarkable happened. As the universe continued expanding and cooling down, it reached a critical temperature where protons and electrons could finally combine to form the first hydrogen atoms. This moment is called recombination, and it's when the cosmic fog suddenly lifted. When this happened, photons were finally free to travel through space without constantly bumping into charged particles. The universe became transparent for the first time, and these ancient photons began their epic journey across the cosmos. These photons, this ancient light, is what we now detect as cosmic background radiation. But here's where it gets really fascinating. When these photons first started their journey, they were incredibly hot and energetic, glowing with the intensity of a star's surface. However, as the universe expanded over billions of years, something called redshift occurred. Just like how the sound of an ambulance siren changes pitch as it moves away from you, light waves get stretched out as space itself expands. This stretching has cooled these ancient photons down to just 2.7 degrees above absolute zero, which is why we now detect them as microwave radiation rather than visible light. The discovery of cosmic background radiation is one of those incredible stories where pure accident led to one of the greatest scientific breakthroughs of all time. Back in 1965, two scientists named Arno Penzias and Robert Wilson were working at Bell Labs in New Jersey with a large horn-shaped antenna. They were trying to eliminate all sources of noise and interference to use the antenna for satellite communications. But no matter what they did, they couldn't get rid of this persistent, annoying static that seemed to come from everywhere in the sky. They checked everything they could think of. They looked for electrical problems. They even cleaned out some pigeons that had been nesting in the antenna, thinking maybe pigeon droppings were causing the interference. But the static remained, constant and unchanging, coming from every direction they pointed the antenna. What Penzias and Wilson didn't realize at first was that they had stumbled upon the most important discovery in cosmology. This wasn't interference at all. This was the echo of creation itself, the leftover heat from the Big Bang that had been predicted by theoretical physicists, but never actually observed. The theoretical foundation for this discovery had actually been laid years earlier by scientists like George Gamow, Ralph Alpher, and Robert Herman. They had predicted that if the Big Bang theory was correct, there should be leftover radiation from the early universe that we could still detect today. But it took Penzias and Wilson's accidental discovery to prove this theory was right. When word got out about their finding, the scientific community was electrified. Here was direct evidence that the Big Bang had actually happened. It wasn't just a theory anymore. It was observable fact. Penzias and Wilson won the Nobel Prize in Physics in 1978 for their discovery, and rightfully so. They had given us our first baby picture of the universe. But the story doesn't end there. The discovery of cosmic background radiation opened up an entirely new field of study. Scientists realized that this ancient light wasn't perfectly uniform. It had tiny temperature variations, incredibly small fluctuations that told the story of how matter first began to clump together in the early universe. These tiny variations, we're talking about temperature differences of just a few millionths of a degree, were like seeds that would eventually grow into the galaxies, stars, and planets we see today. Without these small irregularities in the cosmic background radiation, the universe would have remained perfectly smooth and uniform, with no structure at all. No galaxies, no stars, no planets, and certainly no life. To study these minute variations in detail, scientists launched specialized space missions. The Cosmic Background Explorer, known as COBE, was launched in 1989 and created the first detailed maps of the cosmic background radiation across the entire sky. The results were stunning. The maps showed that while the radiation was incredibly uniform overall, there were indeed those crucial tiny variations that matched theoretical predictions. Then came even more sophisticated missions. The Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001, and later the Planck satellite in 2009, created increasingly detailed maps of this ancient light. These maps are some of the most important scientific images ever captured because they show us what the universe looked like when it was just a baby. Looking at these maps is like looking at the universe's DNA. Every spot and variation tells us something fundamental about how everything we see today came to be. The patterns reveal information about the composition of the universe, its age, its rate of expansion, and even its ultimate fate. One of the most profound implications of cosmic background radiation is what it tells us about the Big Bang theory itself. Before this discovery, there were competing theories about how the universe began. Some scientists favored the steady-state theory, which suggested the universe had always existed in roughly the same form, with new matter constantly being created to fill the space left by expanding galaxies. But cosmic background radiation was the smoking gun that proved the Big Bang theory was correct. The steady-state theory couldn't explain why this leftover heat would exist throughout the universe. Only a hot, dense beginning, followed by expansion and cooling, could account for what we observe. The precision of cosmic background radiation measurements has also allowed scientists to determine the exact composition of our universe with remarkable accuracy. We now know that ordinary matter, the stuff that makes up stars, planets, and us, accounts for only about 5% of the universe. Dark matter makes up about 27%, and dark energy comprises the remaining 68%. These numbers come directly from analyzing the patterns in cosmic background radiation. This discovery has also helped us nail down the age of the universe with incredible precision. By studying the cosmic background radiation, we can determine that the universe is 13.8 billion years old, give or take about 40 million years. That's an amazingly precise measurement for something as vast and ancient as the entire universe. But perhaps most remarkably, cosmic background radiation connects us directly to the moment when the universe first became transparent. Every time we detect these ancient photons, we're literally seeing the universe as it was nearly 14 billion years ago. It's the oldest light in the universe, and it's still reaching us today. Think about that for a moment. The photons hitting cosmic background radiation detectors right now have been traveling through space since long before our solar system even existed. They've witnessed the formation of the first stars and galaxies, They've traveled past countless cosmic events and phenomena, and now they're ending their epic journey by being detected by human instruments on a small rocky planet orbiting an ordinary star. The study of cosmic background radiation has also revealed something fascinating about the geometry of space itself. The measurements show that space is remarkably flat on large scales, meaning that parallel lines remain parallel even over cosmic distances. This flatness is another piece of evidence supporting our understanding of cosmic inflation, a period of extremely rapid expansion that occurred in the first fraction of a second after the Big Bang. Modern research into cosmic background radiation continues to push the boundaries of what we can learn about our universe. Scientists are now looking for even subtler signals hidden within this ancient light. They're searching for evidence of gravitational waves from the early universe, signs of cosmic strings, and other exotic phenomena that might have left their mark on the cosmic background radiation. One particularly exciting area of research involves looking for polarization patterns in the cosmic background radiation. Just like sunglasses can filter light based on its polarization, scientists can analyze how the ancient light is polarized to learn about conditions in the early universe that we couldn't detect any other way. There's also ongoing research into what are called B modes in the cosmic background radiation. These are specific polarization patterns that would be direct evidence of gravitational waves generated during cosmic inflation. Detecting these B modes would be another monumental discovery, providing direct evidence for what happened in the first tiny fraction of a second after the Big Bang. The technology used to study cosmic background radiation has also led to advances in many other fields. The sensitive detectors and data analysis techniques developed for cosmic background radiation research have found applications in medical imaging, materials science, and other areas of physics and engineering. What's truly amazing is that we can study cosmic background radiation from right here on Earth, and even from space-based observatories in our own solar system, yet learn about events that happened nearly 14 billion years ago across the entire observable universe. It's like cosmic archaeology, using light itself as our artifact to understand the deepest history of everything that exists. The implications of cosmic background radiation go beyond just understanding the past. The detailed measurements help us predict the future of the universe as well. Based on what we see in the cosmic background radiation, we can model how the universe will continue to evolve over the next billions of years. As we look toward the future of cosmic background radiation research, scientists are planning even more sensitive instruments and space missions. These will allow us to detect even fainter signals and study even more subtle effects in this ancient light. Each improvement in our ability to measure cosmic background radiation brings new discoveries about the fundamental nature of reality itself. The discovery and study of cosmic background radiation represents one of humanity's greatest intellectual achievements. We've managed to detect and analyze light that has been traveling since the universe was in its cosmic infancy. And from this ancient signal, we've learned the age, composition, and history of everything that exists. Every time you see static on an old television or radio, remember that hidden within that noise is the faint whisper of creation itself, the leftover glow from the birth of our universe. Cosmic background radiation is our direct connection to the Big Bang, proof that we live in a universe that had a beginning, evolved over time, and continues to expand and change today. This discovery has fundamentally changed how we see ourselves in the cosmos. We're not just observers of the universe. We're made from elements forged in stars that formed from the tiny variations we see in cosmic background radiation. In a very real sense, we are the universe becoming conscious of itself, able to look back at its own beginning and understand the processes that led to our existence. The story of cosmic background radiation reminds us that some of the most profound discoveries come from careful observation and a kangai, willingness to investigate unexpected results. Penzias and Wilson thought they were dealing with an annoying source of interference, but they had actually found the key to understanding the entire universe. So the next time you look up at the night sky, remember that surrounding us always, invisible to our eyes but detectable with the right instruments, is this ancient light carrying messages from the dawn of time itself. Cosmic background radiation is truly the universe's baby picture, and we're incredibly fortunate to live at a time when we have the technology and knowledge to see it clearly.